Hello, AP Chemistry students. We're now at section 2.5 on Lewis diagrams. So our learning objective for this one is relatively straightforward. We're going to be representing a molecule with a Lewis diagram. Lewis diagrams are also called Lewis structures or structural formulas. And these are the representations of molecules where you have the atoms represented by their chemical symbols, attached by lines representing bonds, and then surrounded by dots representing electrons. And for this, I like to do a very particular method, which I call the systematic method of drawing Lewis diagrams. And it's systematic because it's a list of steps that you can take. And I think it works for basically any covalently bonded molecule. So to practice, let's draw some structures of oxygen difluoride, nitrate, and ammonium. So our first step is to sum up the valence electrons for each of the atoms involved. For oxygen difluoride, we have 6 for oxygen, 7 for fluorine times 2, gives us a total of 20. For nitrate, we have 5 for the nitrogen, 6 for each oxygen, and there's 3 of them. And then for ammonium, we have 5 from nitrogen, 1 from hydrogen, times 4. And then step 2 is if it has a negative charge, we need to add electrons to the total because a negative charge means we have more electrons than expected. For nitrate, we have a -1 charge, so we add an electron. So we have a total of 24 for that. If the charge is positive, we need to subtract electrons because positive charge means that electrons were lost. We have less electrons than we expect. So for ammonium, we subtract 1 electron, which brings us to a total of 8. All right, for step 3, we're going to draw a skeleton of a structure by putting the least electronegative atom in the middle as sort of our anchor or our spine of our skeleton. And that's going to start to connect everything with single bonds. And as we do this, we need to take note of how many electrons that we've used so far because we have a budget for each of these. And also one quick note, hydrogen cannot go in the middle because it can only make 1 bond. It can only get up to 2 total valence electrons. So for our oxygen difluoride, we put the oxygen in the middle, being the less electronegative atom, and we make 1 single bond with each of the fluorines. And each bond represents 2 electrons, so we're going to subtract 4 from the total. For nitrate, we put nitrogen in the center, connect one bond to each oxygen. That uses up a total of 6. And then for ammonium, we put nitrogen in the center since it can make more bonds than hydrogen. And then we make 1 bond with each of the hydrogens, uses up a total of 8 electrons. And for this one, we've already run out of electrons in our budget. So let's hope that that's a valid structure already. But we'll analyze that in a moment. All right, for step 4, now we're going to add electrons to these surrounding atoms until each has an octet. We start with the surrounding atoms because they're the more electronegative ones. They're the ones that are more likely to pull on the electrons. And what I mean by octet is 8 total valence electrons. For the case of most nonmetals, this is going to be what it needs to get a full shell and be more stable. However, the 2 exceptions to that are hydrogen, which only needs 2, and boron, which only needs 6. And then phosphorus, chlorine, that kind of stuff can do a little bit of weird stuff, but we'll talk about that later. All right, so for OF2, let's focus on our fluorines first. They both already had 2 electrons by having 1 covalent bond with oxygen, in which 2 electrons were shared. So we only need to add 2, 4, 6 for each of them. So that uses up a total of 12 electrons. So we have 4 electrons in our budget left for OF2. For nitrate, we're going to focus on our oxygens. Each of them are going to need 6 since they already have a bond with nitrogen. So 6, 12, 18. And we've actually run out of electrons for this one now since we already used up 6 and we've already used up our whole 24. So we're going to have to evaluate if that's a valid structure. In this one, we already ran out of electrons, so we don't need to do anything for this step for ammonium. All right, next we're going to add any remaining electrons to the central atom. So OF2 still had 4 electrons left, and the central atom only had 4 electrons. So to get 4 more, we just put 2 lone pairs on the oxygen. And this seems like a pretty valid structure now because we have 8 on the fluorine, 8 on the oxygen, and 8 on the fluorine, and we've used exactly the amount of electrons allotted to us in our valence electron budget. All right, for nitrate, we have no electrons left. And this is going to be a little bit of a problem that we need to address because if we look at the nitrogen in the center, it only has 6. It needs 2 more electrons, but it doesn't have any electrons left. But we'll address that in the next step. Ammonium, once again, we can skip this step because we've already run out of electrons. All right, step 6, if the central atom has fewer than 8 electrons, which we just noted was the case for the nitrate molecule, we're going to remove an electron pair from an outer atom and add another bond between the outer atom and the central one until it has a complete octet. So we noted that the nitrogen needed 2 more electrons, so it's going to need to make another bond with one of the oxygens. So what we can do is, in this case, we could take like a lone pair of oxygens from, lone pair of electrons from this oxygen, and then turn it into a double bond now with the nitrogen. And then we end up with this structure. And this is now a valid structure because it has 2, 4, 6, 8 for that oxygen, 2, 4, 6, 8 for the nitrogen, and then both of these oxygens have 8 as well. And when you're doing this step, note that period 3 elements like phosphorus, sulfur, and chlorine, they can get up to 14 electrons. They can get what's called an expanded octet, but I'm going to talk a little bit more about that in the next lecture. All right, let's do some more practice. Let's draw FCN. I forget what this molecule's actual name is, but we have a fluorine, a carbon, and a nitrogen. And let's go through our steps again. So step 1, let's sum up our valence electrons. We got 7 plus 4 plus 5, total of 16. Now let's make a skeleton. We put the carbon in the middle, being the least electronegative of the 3. Make a single bond with each of the other atoms. That uses up 4 electrons. We have 12 left. Now we add our electrons to the outer atoms till they get 8. So we got 2, 4, 6 on this fluorine, and then 2, 4, 6 on this nitrogen. They both have 8 now. Our carbon only has 4, so we're going to do something with that. And we've run out of electrons. We've already expended our whole budget. So we're going to need to do something with carbon in order to get it up to 8. And we need to figure out how we're going to do this because fluorine technically only makes one bond because it has 7 valence electrons. So we're going to need to lean on the nitrogen this time. You'll never see any cases where fluorine makes double or triple bonds. Fluorine is the most electronegative element. It is really greedy with its electrons. So never expect fluorine to form more than one bond. Nitrogen, however, has 5 valence electrons. It usually needs 3, so making 3 bonds with nitrogen is pretty common. So we're going to take 2 of our lone pairs and turn them into bonds. So now we're going to end up with a triple bond between carbon and nitrogen. And now let's check if everything's valid. We got 8 on the fluorine, 2, 4, 6, 8 on the carbon, and then 2, 4, 6, 8 on the nitrogen. So this looks like a good structure for FCN. All right, let's try something a little bit more complex, and complex meaning many atoms involved. The more complicated the molecule, is the harder it is to kind of like figure out what the structure is going to look like. So in this case, a lot of the chemical formulas of more complex molecules are written in a way that gives us a hint at their structure. You'll notice that instead of saying C2 H3O2, we called this molecule CH3COO minus. And this gives us a hint at the structure. We can assume that 3 hydrogens are going to be attached to 1 carbon, and then 2 oxygens are going to be attached to carbon, or at least coming after the carbon. So we have a couple options here to draw this acetate molecule. So let's do the first step. Let's count up our valence electrons. We got 4 times 2 for the carbon. We got 1 times 3 for the hydrogen, 6 times 2 for the oxygen, and then plus 1 because of the charge. We have a total of 24 electrons to work with here. So I noted here that because of the way the molecule is written, it gives us a clue into the structure, but we don't know for sure what that means. So I drew 2 possible options here. One where we have carbon, carbon, oxygen, oxygen all in a chain, and then another one where we have the 2 oxygens attached to the carbon. Based off of this, it's unclear which one it is, but we could probably figure out which one it is when we start drawing it and like seeing what works. So we've used up 12 electrons for each case. I'm keeping a tally up here instead since we have 2 different structures. Okay, now we're going to add our extra electrons. I'm starting with the more electronegative ones. So for this one, I started with 2, 4, 6, 8, 12. And then I add 1 extra pair. Wait, 2, 4, 6, 8, 10, 12. Yeah. And I ended up putting a lone pair on the carbon. And it's still 2, 4, 6. This carbon's still not happy, so it's going to need like a double bond or something like that. This structure is already not looking great. One thing I'll note is carbon is not super electronegative, and it's rarely ever going to get lone pairs on it unless it literally has to. A good example of that is cyanide, Cn minus, where you're going to have a lone pair on the carbon. But I'm already losing confidence in this molecule. But let's look at this one. 246, 246. We put 6 electrons on each of these oxygens. They both look good. This carbon has 2, 4, 6. And I think we could easily make a double bond with one of these oxygens, which I do now here. I take this lone pair of electrons and turn it into a double bond. And this one looks good now. I think this one was just too much of a lost cause. That we're going to have to do some weird stuff that is not normally occurring with these types of elements. So I kind of abandoned that one. So here we are with our final structure of acetate. And you'll notice that I took a pair of electrons from this oxygen, but I could have also easily taken electrons off of this oxygen and made a double bond here instead. And the thing I'm going to say about this is both of these structures are actually equivalent and occurring simultaneously. This is something called resonance, which I'm going to talk a lot about in the next group of slides. So finally here, I did want to address one major limitation of Lewis diagrams or Lewis structures, is that if you have an odd number of electrons, your octet rule is going to be impossible to satisfy. So nitrogen dioxide is a really good example of this. Because we have 17 electrons, we're going to end up with 1 electron left over on the nitrogen. That's not even a pair, and this nitrogen still only has 7 electrons. And that is honestly true to real life of what this molecule looks like. And this molecule has a particular reactivity because of it. So just note that some things with odd amounts of electrons aren't going to have perfect structures where everything has a full octet. All right, so that is Lewis diagrams, and I'll see you in the next slideshow.